Alright, so let's start with a summary of last week. So I just have to get my notes together here. Alright, so we had seen that one could introduce what we call the generalized momentum as a partial derivative of the Lagrangian with respect to the Qi dot. So we call that the generalized momentum. And it's the conjugate momentum to Qi. And so as we move forward, we'll see that each coordinate has a conjugate momentum pi that you can define. We also noted that from the Euler-Lagrange equation that if the Lagrangian didn't depend explicitly on Qi, so if the partial derivative of the Lagrangian with respect to Qi was equal to 0, then the associated conjugate momentum was conserved or a constant. And then we did some examples, and we saw that depending on the choice of coordinates, some coordinates would be cyclic and some wouldn't, leading to conserved momenta, and some choices of coordinate systems would not lead to conserved momenta. And so the question arises, is there a way to figure out what quantities are conserved? On the one hand, something that we'll explore further is there a perfect choice of coordinate system where all the coordinates are cyclic and thus all the momenta, conjugate momenta, are conserved? And that we'll look at later. But for now, we want to see, is there a general method that allows us to find the conserved quantities given a Lagrangian? And so we introduced the concept of a continuous transformation and a continuous transformation of the coordinates is a transformation of the coordinates that can be built up as the sum of a bunch of infinitesimal coordinate transformations. So that means that you could have a new set of coordinates, Qi primed, which are a function of the Qi dots time and some parameter epsilon. And that parameter epsilon can be varied continuously. So you can make that transformation as small as possible. So for example, you can imagine a rotation through a finite angle to be the sum of a bunch of rotations through infinitesimally small angles. And so if you can break up a transformation into a bunch of little transformations, it's a continuous transformation. And you can parametrize that by adding in this parameter epsilon. Okay? And so we also wrote out the infinitesimal transformation. We introduced a new notation. For an infinitesimal transformation, we wrote that the Qi primed was equal to the Qi plus the delta Qi, and we chose to write that as Qi plus some function fi of the coordinates times delta epsilon. And in principle, we can also allow t to transform. So we say that t prime would be t plus delta t, or t plus some parameter g, which again can depend on the quantities qi dot, and t times delta epsilon. So functionally, the transformation for the time and the position coordinates are the same, but we decided to distinguish them as being a function f and a function g for time. And then we started to look at what's called Noether's theorem. And Noether's theorem tells us that each continuous transformation that leaves the action unchanged leads to a conserved quantity, which we call a charge, Q. Okay? And so if we define delta S to be the integral, so it's a modified action minus the unmodified action. So the modified action would be an integral from TA to delta TA, from TA plus delta TA to TB plus delta TB of the modified Lagrangian. So it's the Lagrangian of the transformed quantities. So that would be a Lagrangian as a function of Qi plus delta Qi primed, Qi dot plus delta Qi dot primed, T minus the unmodified action, so the integral from TA to TB. Sorry, I forgot the dt at the end there. Of L of Qi dot T dt. So if delta S equals 0, then there exists a quantity Q that is constant. The E that's facing backwards means there exists. And the goal of this lecture is to prove this and to figure out what that quantity Q is that's conserved. Okay, so in this delta S, this first integral here is the action after some infinitesimal spelled a little bit wrong, transformation. Okay? So you have some infinitesimal transformation of the Q's that gives you a bunch of Q primes, so you can calculate this new Lagrangian. The most general transformation is also going to transform time. So that very general transformation is given by specifying all the F's and the G. So then you can calculate a new action. So the integral, so the Lagrangian has to be calculated with these new variables. And then the limits on the integral are the transformed time. So that's the transformed action minus the untransformed action would be equal to 0. So that means that the action is invariant to this transformation. And mathematically, when we say the action is invariant to this transformation, it means that the action calculated after transformation minus the action without the transformation is equal to 0. Okay? So today we're going to do the math to calculate delta S and figure out what Q is and show that it's conserved. So I'll make the note again that I'm writing, Qi primed is equal to Qi plus delta Qi primed, not Qi plus delta Qi, which is what we had before. And the reason is that we're not only varying the Qi, we're also varying time. Right? And Qi prime in principle is a function of the Qi dots, and time. So this delta Qi primed here is the normal delta Qi, which we've written as Fi delta epsilon, plus a Qi dot delta t, plus terms that are higher in order in delta Q and delta t. So it's simply a Taylor series expansion, taking into account that the Qi prime depends on both the Q's and T's. And so if you're varying both the Q's and the T's, you have to do terms that have delta Q's and delta T's in them. Okay? And we're going to take, as usual, the approach that the higher order terms are roughly equal to 0. And so we'll need that in about a half an hour probably. So before proceeding, we're going to consider an identity. Okay. So given a function, a very general function, f that depends on the Qi, the Qi dots, and t. Of course, when I say it depends on Qi, I mean it depends on Q1, Q2, Q3, Qn, and the Qi dots, and Q1 dot, all the way to Qn dot. Okay. So let's say we're given a function, and its antiderivative capital F of Qi dots, and t. So what I mean that d capital F by dt is equal to little f. All right. So consider this integral. Consider the integral from Ta to Tb of little f dt minus the integral from Ta plus delta Ta to Tb plus delta Tb of f dt. Okay, so the goal is I want to get rid of the limits that have the delta t's in them. So let's consider this difference. So very generally, right, that's equal to, if I look at the first integral, that's big F evaluated at Tb minus big F evaluated at Ta minus big F evaluated at TB plus delta TB minus big F evaluated at TA plus delta TA. Alright, since the integral of little f is big F, then a definite integral is just given by evaluating f at the different values. If I just expand this to switch one of the negative signs, then I have capital F evaluated at TB minus capital F evaluated at TA minus capital F evaluated at TB plus delta TB plus capital F evaluated at TA plus delta TA. Okay?
In the notes, you have that flip-flopped, and you started with TA minus F of TB. These aren't equivalent expressions, so which is correct?
In the notes you're saying this is wrong?
Yeah, they're exactly flip-flopped. You have F of TA minus F of TB minus F of the quantity TA plus delta TA plus F of...
Yes, you're right. In the notes it's flipped. Which one did I do wrong? Oh, it looks like I did it wrong in the notes, right? What I just did now looks correct. Yeah, what I did now is correct. It's in the notes that it's flipped. Does that answer your question? I think it'll cancel in the end. Okay. Thanks for pointing that out. All right. So consider now one of these terms. So consider, for example, capital F evaluated at TA plus delta TA. So we can write that as a Taylor series. And if we write that as a Taylor series, or let me just write it out very explicitly, that F evaluated at TA plus delta TA means that I have to evaluate F, which depends on QI, evaluated at TA plus delta TA. QI dot at TA plus delta TA. And T at TA plus delta TA. So delta TA is small, right? So I can evaluate that as a Taylor series expanded about F at TA. So that's equal to F at TA plus the total derivative dF by dt delta TA. All right. In the notes, I expanded the dF by dt using the chain rule, but then I don't know why I did that in the notes, because in the end you really just need the total derivative. Okay, so that's just the Taylor series plus terms that are small. So I can also write that as F of TA, capital F of TA, plus df by dt times delta t evaluated at TA. And I can also write that as capital F of TA plus, now d capital F by dt is little f, right? So it's capital F evaluated at TA plus little f times delta t, then evaluated at TA. Uh-oh, I think my screen has gone crazy. It's done this in the past, and the answer has been to have to reboot. Alright, I'll try to keep going, but if it goes crazy, then I'll have to reboot for a couple minutes. Okay. So let's rewrite the expression we had above using what we just found. Oops. So that means that the thing we were calculating, which was the integral from TA to TB of f dt minus the integral of going from TA plus delta TA to TB plus delta TB of f dt. So now writing what I had above, so that was capital F at TB minus capital F at TA minus, this is going to be all wrong in the notes, I hope it works out to the right answer, minus capital F evaluated at TB plus delta TB plus capital F evaluated at TA plus delta TA. And now I plug in what we just derived, so I have F of TB minus capital F at TA minus capital F at TB plus minus, I guess, little f delta t evaluated at TB, sorry. Plus capital F evaluated at TA plus little f delta t evaluated at TA. Okay. So now we have the capital F's evaluated, the TA's and TB's cancel. Because I have F at capital F at TB minus capital F at TB. Right. So this term cancels with that one. And the FTA terms cancel as well. And so that's equal, that's equal to little f times delta t evaluated at TA minus, that'll have delta t evaluated at TB. I'm a little bit confused why the sign is wrong in the notes. So I'm going to write that as the integral from TA to TB of d by dt of f delta t dt. Now that's what I have in the notes, but for this to be correct here, it looks like I need a minus sign. But I hope there's another mistake in the notes that cancels that minus sign. Otherwise we're going to have a problem. And the subscripts switch to the entire derivation in the notes. Hopefully also in the next part. I guess we'll find out. I'll have to do it in my head now as we go. All right. So hopefully this last part was okay, right? Because I just added an integral and a derivative sign, so they just cancel each other. All right. And so ultimately, the whole point of this was to find this identity that the thing I had, which was the integral from TA to TB of f dt minus the integral from TA plus delta TA to TB plus delta TB of f dt is equal to minus the integral from TA to TB of d by dt of f delta t dt. And the whole point of this was so that I could write out the integral from TA to delta TA, from TA plus delta TA to TB plus delta TB of f dt. So just rearranging the equation I have, that's equal to the integral from TA to TB of f dt minus the integral TA to TB of d by dt of f delta t dt. That's the whole point of this, is so that I can remove the delta t's from the limits of the integral by writing it as two different integrals.
Yep, that's wrong. It needs to have a plus.
Yes. That's right. Because now it looks like in the notes. I tried to sneak that in there, but you guys caught me. Okay. So remember what the point was. Initially, the point was to go back and look at this change in the action. Right, so in Noether's theorem tells us that if the action is unchanged by this transformation of variables, then there's a conserved quantity. And so the whole point of this initial identity was so that I could rewrite this first term in delta S differently. Okay? So let's look now at that first term in delta S. So that first term in delta S was the integral from TA plus delta TA to TB plus delta TB of L evaluated at QI plus delta QI primed dot plus delta QI dot primed T dt. Okay. So I'm going to write that as a Taylor series. I'm going to expand L, which is the value at QI plus delta QI prime plus delta QI prime. I'm going to expand L in a Taylor series about QI and QI dot prime. Okay, so this is going to equal the integral of from TA plus delta TA to TB plus delta TB. Now I expand this in a Taylor series, so it's L. Sorry, I have an extra prime there as well. In the top part, it's QI plus delta QI prime, QI dot plus delta QI dot primed. Okay. So that's L evaluated at QI dot and T plus the Taylor series which I'm going to write as the sum from I equals 1 to n. So it's all the partial derivatives, right? And there's multiple QIs. So the sum is over all the possible QIs. So we have di-L by di-QI, delta QI primed, plus di-L di-QI dot, delta QI dot prime, plus higher order terms, and the whole thing dt. Why does it keep opening this? Okay, so remember from the Euler-Lagrange equation that di-L by di-QI dot, this thing here, is actually equal to PI. And this thing here, di-L by di-QI, is actually equal to PI dot. Any questions about that? Because the Euler-Lagrange equation, let me just go write that in the summary, just in case. The Euler-Lagrange equation is d by dt of di-L by di-QI dot minus di-L by di-QI equals 0, right? So that term is PI. So this is the same as saying that PI dot is equal to di-L by di-QI. Okay? So I'm going to make those two substitutions. So this is equal to the integral from TA plus delta TA, TB plus delta TB, of L at QI dot T plus the sum of I equals 1 to N of PI dot delta QI primed plus PI delta QI dot primed. Okay, screen is going crazy again. Okay. I apologize for the screen going crazy. Okay, so now you can recognize this PI dot delta QI prime plus PI delta QI dot prime. That is the product rule of the derivative. So I can rewrite this as, I'll write the first part of the integral here. Integral from TA plus delta TA to TB plus delta TB of L evaluated at QI dot T plus, now I'm going to write this as the derivative product rule. That's the same as d by dt of the sum I equals 1 to n of pi delta qi primed. Alright, so if I take the derivative of the thing I have there in parentheses after the sum, then I get the thing that I have above, right, using the product rule for derivatives. Okay. So now I'm going to use the identity that I had before. So now we have this integral that goes with the limits TA to delta TA and TB plus delta TB, and we derived that identity that allowed us to write this as the sum of two integrals whereas the integrals go from TA to TB and don't have any deltas in them. Okay. So if I do that, I get the integral from TA to TB. So the first thing, well, it's actually at the top of this page, isn't it? The first thing is the integral unchanged. So the integral unchanged is, or the integrand unchanged, I should say, L at QI dot T plus d by dt of the sum I equals 1 to n of pi delta qi primed. And so this should now be plus okay. I'm going to reboot my computer because it's getting a little bit unwieldy, and I imagine it's very hard for you guys to follow as well. So give me, 3 minutes to reboot this thing, and then hopefully it starts working. All right. Okay, I think people can hear me again. Hopefully it goes better. I'm not convinced. Oops. All right, so still not completely working. Okay. All right, so we introduced the identity, and I wrote out the first term, which is the integral unchanged, and then the second term is the integral from TA to TB of d by dt, the integral unchanged, delta t dt, right? So it's d by dt of the integrands, which was L qi dot t plus d by dt of the sum I equals 1 to n of pi delta qi primed dt, and then this whole thing here is times delta t. Oops, that dt goes on the outside there. Now, this term here, the second term, right, the second integral I have a d by dt of L, integral dt. Then I have d by dt of the sum of pi delta qi times delta t. So the first term is L, has an L delta t, so it's first orders in deltas, whereas the second term, the one with the sum, is second order. It has a delta qi primed and a delta t. And so that's small. So this term here, we have a delta qi multiplied with a delta t, so that's going to be roughly equal to 0. So I'm going to rewrite that. So dropping that term. We get that the action evaluated at the transformed action is equal to the integral from TA to TB of So it's just that first term that we had, L of L at QI, QI dot, and T, plus d by dt of the sum of the pi delta qi primed dt plus the integral from ta to tb of d by dt L at qi, qi dot, and t delta t dt. Okay? So this allows us to now calculate delta S. So delta S is what we have above minus the unvaried action, which is valued at the normal L. So rewriting the term that I have above, do I really want to, yeah, I guess I'll rewrite the whole thing. All right, so we have integral from TA to TB of L at QI, QI dot T plus d by dt of the sum of pi delta qi primed dt. Still having some problems with my tablet here. Plus the integral from TA to TB of d by dt of L at QI, QI dot T delta T. dt, that's just the first term, and then minus the integral of L at QI, so that's the unvaried QI dot T dt. That's from TA to TB. So that's now delta S. So it's the same term as above minus the normal Lagrangian action. Okay. So the term with the L's cancels. All right, so this term cancels the last term. And we're left with the integral from TA to TB of d by dt of the sum of the pi delta qi primed dt I forget a term. Nope, I didn't forget a term. Plus, like in the notes, well, let me just group them, right? Because the next term now is d by dt of L of qi dot t delta t. Right, so both these terms have a d by dt, so I'm just going to put the d by dt in front. And then the second term becomes L evaluated at qi dot t times delta t. dt. Okay. So now remember earlier I made this point of the delta qi primed was actually equal to the delta qi plus qi dot delta t. All right. So if I expand that out, I have the integral from TA to TB. Still having problems with my stylus here, it's not catching. Okay. The integral from TA to TB, d by dt, what is wrong with this thing? Of the sum from I equals 1 to n of pi delta qi, right, dt, so that's the first term. The second term is the sum from I equals 1 to n of pi qi dot delta t, and then the last term is the Lagrangian L at qi dot t delta t, the whole thing dt. So let me just group the terms that have delta t's together. Okay. So that's the integral from TA to TB of d by dt. So in the first term I have the sum from I equals 1 to n of the pi delta qi, and then plus the sum from I equals 1 to n of pi qi dot plus L evaluated at qi dot and t. So that whole thing times delta t dt. So now Noether's theorem tells us that if this thing equals 0, there's a conserved quantity. Right? This is the variant, the change in the action from the continuous transformation. So if delta S equals 0, What's wrong with this one? So if delta S equals 0, the thing in square brackets is equal to a constant. Then the sum from I equals 1 to n of pi delta qi plus the sum of pi qi dot plus L of qi dot and t times delta t equals a constant. Now, somewhere along the way, we must have made a mistake, because this should be a minus. So if you can find where the mistake is, please tell me. Otherwise, it's going to be my homework for the next lecture to figure out why that's a plus in this latest derivation. But the answer in the notes is correct. But clearly we did have a mistake in the notes at one point. So there's got to be some other mistake somewhere else that fixes it. Okay? So I apologize for that. And so what we find is that, I'm not going to write it out correctly, well, what I know the answer should be. Oops. So if we introduce the quantity Q, capital Q, as this sum from I equals 1 to n of pi delta qi plus the sum of pi qi dot minus L delta t. That quantity Q is conserved if the Lagrangian is invariant with respect, if the action is invariant with respect to that change in coordinates. And so we can write this. Recall that if we write the qi primed to be qi plus delta qi, or qi plus fi delta epsilon, and explicitly I'm implying that t prime can be written as t plus g delta epsilon. Then I can write this conserved quantity Q, the big capital Q, as the sum of the I equals 1 to n of the pi fi plus the sum from I equals 1 to n of pi qi dot minus L times g. So I've rewritten the delta qi as fi delta epsilon, and I've written the delta t as g delta epsilon, and delta epsilon is now the same in both terms, and so it can just be dropped, right? So what I did was I went tablet is really misbehaving. QI, I wrote delta QI as Fi delta epsilon, and I wrote delta T as G delta epsilon. And then I just dropped the delta epsilons, since they are arbitrary. So a constant divided by another arbitrary constant is still a constant. Or they would have factored out the integral that was equal to 0. So we can specify any infinitesimal transformation by specifying the f's and the g's. So given a transformation where we specify the f and the g's, if we find that the action or the Lagrangian is invariant with respect to that transformation, then we know that the q written as such is a conserved quantity. And if you look at it a little bit more carefully, the second term, this thing here, is the Jacobi integral. And that's the quantity that we found to be conserved when the Lagrangian was invariant with respect to time. And we found in that case that it was actually equal to the total energy. So that term G is the term that's associated with a transformation in time. So the Lagrangian is invariant to a transformation in time. So if we shift time by an arbitrary amount, that means that G equals to 1. Then the conserved quantity, if the f's are all equal to 0, is simply the Jacobi integral, or the total energy. So here we see a much more fundamental case of how symmetries in time or transformations that are related to time are related to a conserved quantity that we've already seen can be related to energy. So let's do a more simple case. Now that we did the general derivation, let's do a simple derivation where we only consider variation of the coordinates, not of time. So consider a coordinate transformation. So explicitly we're saying that G equals 0. That means that we can write out the Qi primed simply as Qi plus Fi delta epsilon and so here we don't have to write in the term that has the delta T in it. And if we look at how the Lagrangian changes, the variation of the Lagrangian, I'm sorry, that's almost impossible to write on this tablet at this point. We can write the variation of the Lagrangian using the chain rule. So that's diL by diQi delta Qi plus diL by diQi dot delta Qi dot. So clearly if delta L equals 0, then delta S equals 0. So in this specific case of just the coordinate transformations, we can get the answer just by looking at delta L. So let me just write that out as a sentence. If delta L equals 0, oh, that's right. then delta S equals 0. So let me rewrite delta L. Sum of I equals 1 to n. So the diL by diQi, remember, we can write that as pi dot. So here we have pi dot delta Qi plus, remember, the diL by diQi dot we can write as pi. That's the definition of pi. And so this is the exact term we had earlier in our integral. So we can write this as the time derivative of the sum from I equals 1 to n of pi delta Qi. And so we can write that using the fact that delta Qi is Fi delta epsilon. All right. So that's d by dt of delta epsilon, the sum from I equals 1 to n of pi Fi and so if delta L equals 0, then this is true regardless of the choice of delta epsilon, right? And so that means that d by dt of the sum of pi Fi is equal to 0. In other words, pi Fi the sum of the pi Fi must be constant. So thus, if we introduce Q as the sum of the I equals 1 to n of pi Fi, that's equal to a constant if delta L equals 0. And so that's just the first term in the Q that we found for the more general case. All right.
Dr. Ryan? Okay.
Yep.
That first line where you have your delta L equals the sum, the last Qi term, the delta Qi, isn't that a Q dot I? Okay.
Should have a dot. Yes.
And then you make the move to the next expression because that's the same as the product rule.
Yes.
Okay, good. Thanks.
Okay. So I hope the summary will be more useful when I start the lecture next time. Sorry, I had a lot of trouble with the tablet today. And on top of that, that minus sign in the derivation threw me off. So if anyone can find what the error was, otherwise I'll try to figure it out for next week. Okay, so I'll stop here because it's almost unusable, my tablet, at this point. And next, on Wednesday, I guess, we'll just do a couple of examples of finding what these conserved quantities are. And then we'll move on to the Hamiltonian. Okay, any more questions about this? Okay, so I'll talk to you all on Wednesday. Thanks, everyone.